Okay, great. Can people hear me at the back? Okay, so yeah, this is this sort of a result of work that has been happening over many years, and it's now in a mature enough state that we've been able to put it into open source software and libraries and so on. So that's what I'll be talking about today. We'll try to keep it fairly interactive, so feel free to interrupt me with questions if you have them at any point. And as you might notice, the effort has involved a lot of people. Um, right now, all of them are at Microsoft Research, so this has been a huge team effort. So I'll explain everything in the context of a running example, one of recommendation in the scenario of personalized news. So basically, you're running, let's say MSN in this case. So users arrive. We have some demographic information on the user, perhaps if they're logged in. We have their browsing history, time of day, and so on. So we have all of this contextual information available. And based on that, you would like to recommend some news articles to display to this user. So that's what the website renders. And then the user responds. Maybe they read some articles. Maybe they just sort of get bored and leave the website. And you get to observe this signal, right? And kind of the overarching goal of any content recommendation service is to choose content that leads to desired user behavior, whatever you have in mind, improve your long-term engagement, improve sort of user visits, and so on. So that's kind of the high-level setup that we're interested in. I'll spell out more details as we go along. So we've kind of I'll describe how we approach this using machine learning, but just to give first a summary of what can be done in these sorts of scenarios. So this we actually did. So we've been building a tool we call the Decision Service that we did deploy in the MSN scenario a few months back, and these are some of the results that we collected, where you see roughly there's on average about 25% improvement on a daily basis in the So this is in the number of clicks, and then they of course collect a bunch of different user engagement metrics, and kind of across the board there were pretty substantial gains, and the system is now basically powering all of the news recommendations for MSN. So that's kind of one example, and I'll talk you through about what does the system do, what are the underlying machine learning formalisms, and so on in the remainder of this talk. Okay, so basically this is the scientific problem here. It's been developing under the moniker of contextual bandits for the last several years. So the basic idea, oops, I see there's been a Windows to Mac issue with the math fonts. We'll try to power through it. Okay, so so we observe a context that is xt, right? So what the context is all the information that we have at this moment about the world that is relevant to the decision we want to make. So if you're doing news recommendation, it's all the information you might have about the user and about whatever else relevant you need to know at this time. If you're thinking more like personalized medicine, it's all of the information you might have about the patient, all of the medical history, all of the lab tests you've run on the patient. If you're doing more a Netflix type scenario, then it'll be all of the previous the previous feedback the user has provided you, all of the previous content they've watched, and so on, right? So that's kind of all of the information that's relevant to the decision about that you're about to make is what we call context, and that's going to be denoted by xt. Upon observing this xt, we make a recommendation, we select an action, and that will be denoted by little a t. And there might be a varying set of actions. So the action is chosen from some set, which is denoted by capital AT. So for instance, when you're dealing with a news scenario, the set of news articles that are available that are relevant at any point of time keep on changing throughout the day, across the days, and so on. So that's why you can't just say that, oh, there's a fixed set of actions, and you have to deal with a changing set. And finally, upon taking the action, you observe some feedback about whether you actually did something good or not. And we kind of assume here that this reward is kind of reasonably immediate. So it should be, okay, it doesn't necessarily have to be available in real time, but at least it's available at relatively short time scale. If you're interested in how to deal with long-term rewards, I can talk about that later on. So high level, right? So we can try to map all these different quantities to our news recommendation example. So XT are whatever basically features that we have available on the user in terms of maybe what they've read in the past, where which geographic location they're coming from, what's the time of the day currently, and so on, right? So we have all this information that goes into, that's featureized to go into XT. AT, like I said, is the candidate pool of news articles that's available to you at this time. Little a sub t is maybe, so let's for simplicity assume that we're just recommending one news article. Obviously, that's not the case here. When you look at the web page, there's this whole complex layout that's being, oh, marker doesn't show. So yeah, there's this whole complex layout that's being, of course, chosen here. We're not going to worry about how to go from picking one thing to picking a layout. Again, that's something I'm happy to talk to you offline about. And then the reward in this case, let's just take the simplest example, which is click or no click, right? So you get a reward of 1 if your recommended article gets a click. You can again refine that a little bit. Maybe you get a reward only if you get a click and the user spends some time actually reading the news article rather than getting bored right away and leaving it. But again, let's just stick with the simplest case. Right, so, and of course, this is just one example. So recommendation scenarios kind of arise all over. And in fact, you can pretty much at this point, any system that, so I would claim basically if you're using machine learning to do X in the context of a system that serves something to a user, then probably there is a need to use this machinery for you. So I have a few examples on this slide in the context of stuff we run into at Microsoft, and I'm sure there are other things. You can replace Microsoft with a lot of other things also, and you'll see very similar needs. So I'll not dwell on individual examples here. I want to point out some of the high-level properties which actually distinguish this problem from what we are typically used to in standard machine learning, like typical classification or regression problems. So I want to why do we need contextual bandits, right? Why is there a need of a new term, a new formalism here? So let me just spend a few minutes on that. So key property of this problem is that, so you take an action, right? You display an article, you get feedback on it. You do not get feedback on all of the other possible actions that you could have chosen, right? So there is partial information here. And meaning you cannot just go and learn a classifier that sort of picks the best action each time, because you actually don't know what is the best action at each time. You just know here is one action I picked. I know whether it was good or not. I don't know anything about the other actions, right? And so this is pretty unique to these problems. And so now if you sort of want to find the best action in each situation, then intuitively you might feel like you really should be somehow trying all possible actions, or at least all plausible actions, all plausibly good actions each time. But of course, remember, we want to do well. In fact, not just, we don't want to just find sort of the best news article that works for everyone. We actually want to do this in a personalized manner, right? So we want to find the best action to take in every context, the best article for every user, which means just extending the previous argument, you would need to try every plausibly good action for every context. Of course, this is usually not possible because a particular user with a particular browsing history at a particular time of day with a particular set of candidate actions, usually you see them once and never again. So you don't really have the opportunity to try many different things in the same context. So this just, when you first see this, it might appear impossible. In some sense it is. However, there is a very nice probabilistic argument that you can use here. If instead of choosing the actions in a deterministic way, if you choose them in a randomized fashion. So if you assign non-zero probability of choosing every plausibly good action on every context, then at least sort of in an expected sense or in a distributional sense, with some probability you observe feedback on every action, because with some probability you would have taken it and you would have observed what happens. Of course, you observe feedback truly only on one, but there is some probability associated with which you would have received feedback even on the other things. And this is kind of crucial, because this allows us to actually do learning in a correct manner. And there are actually very simple, very intuitive examples that you can construct to show that if you do not do this, if you do not do randomization in these scenarios, then you might just and you do everything else correctly about your machine learning. You know, you sort of collect enough data, you sort of control for overfitting, you do your training test splits properly, do everything else properly according to, you know, what the textbooks tell you. You can learn something horribly wrong. So in fact, so John Lanford, who's one of the collaborators on this project, so he has this blog called hunch.net, and I wrote a blog post on it about why you really need this randomized experimentation in these scenarios a while back. So I'm not going to go through an example like that today, but if you're curious, feel free to go. I think go read the post. I think it was called something like randomized experimentation. And there's also, there are tutorials about this and so on. So the bottom line is, right, if you think about it, there is some kind of a causal feedback loop happening here, right? So we have a system. The system is driving what data we collect. Based on that data, we try and improve the system, right? So if you're not careful, you can run into a lot of delicate issues about correlation versus causation. And so we're going to try to not run into this by using randomization. And let me at least give you a cartoonish picture of what I mean by randomization in this context. So typically you're at a very high level. Your system might look something like a user comes in, you have some sort of a recommendation policy that takes in all the information about the user and maps it into some action, maybe a news article about International Space Station in this case, right? So, okay. And for a different user, maybe you get a different action and so on, right? So that's maybe your status quo recommendation policy. What the decision service might do in this scenario, for instance, it would take your recommendation policy, it would consume that thing, but additionally put some jitter on top of it, add some randomization, and now the article that's displayed to the user is a joint outcome based on the randomization and what your system recommended in the first place. So for instance, maybe with some probability, you still see the same article about space station, but with some other probability, you might see a completely different article about candy canes, right? And with some other probability, you might see a third article for the same user. Even if your underlying recommendation policy was always choosing this article for the user, you now sort of add exploration into the system. You observe, you display different articles and collect feedback on them according to a randomized rule at different times, right? And at a very high level, there is kind of a particular loop that we are trying to create here, and this is kind of I think this is the kind of scenario you want to create almost in every online system that uses machine learning to some degree. So somehow you wanna collect data, but you know, I'm making a case that you want to collect the data in a randomized fashion. So that's what I call explore. So this is data collection. Once you've collected the data, you log it, you learn from the logs, and you deploy the new model, right? And you want to do this over and over again. And if you do this correctly, hopefully your system will constantly improve over time. I have tons of anecdotes where this does not happen. So, you know, the fact that this needs to happen, people realized maybe at least a decade ago that this needs to happen, that you need to randomize here. Exactly how to randomize is something that has been a very active area of research, and which has gained maturity maybe only in the last decade or so. But at least people understood simple ways of doing this. It turns out, even after you realize you need to do this, doing this correctly turns out to be hard in very subtle ways. And in our own experience, we've encountered a lot of frustrating failures where basically, so a very common failure mode is each of these 4 steps is at least owned by a different team in any reasonably sized organization. Often, you know, there are sub-teams and sub-teams even within those, but at least, you know, there is sort of separate, each team, there are separate teams, each team might have different goals, and what one team doesn't end up sufficing for what the other team needs often, in order to create this this cycle in the right way. The step that I've personally actually seen most often is the logging part, which might seem like silly. Logging, you know, is probably the most mundane task, we think, amongst all of the things necessary for machine learning. But there are a lot of very intricate failures that happen in the logging step in our experience when we are trying to do these randomized experiments. I'm not going into the details here. Again, I have a lot of anecdotes that I can share if you're curious. And then there are also a lot of the systems are not designed to support randomized decisions, right? So that's another place where we often run into trouble. And basically, what ends up happening is that you go in with very good intentions, you know the correct signs, you try to create the right system, and still you end up creating a system that doesn't work as it should. So after sort of failing at this several times, we decided, okay, you know, maybe if you want something done right, you should do it yourself. And that was a feeling that led to the creation of this decision service tool that I'm going to be talking for the rest of this talk about. So the goal of decision service is to basically make this virtuous cycle of exploring, logging, learning, and deploying very easy to create. It should be very efficient because we want to run this at scale. It should be as automatable as possible because we really want, ideally, if possible, to even do this without a data scientist in the loop, although that in most practical cases that turns out to not be true. And we want to keep things fairly modular. So maybe, you know, you're sort of organizationally invested into doing some aspects of this cycle in a particular way, but we still want to be able to let you benefit from the others. Okay, so we've created a general purpose system to try and do this, and this is what the system roughly looks like at a very high level. So let's say you have you have an application, right? That's the leftmost box here. So the only piece of the system that your application needs to interface with is what we call the client library, or now we also have a web API of the system actually. So this is kind of the front end of our system, which interfaces with an application. And roughly the way it interfaces is, so, you know, we talked about sort of observing context, taking a decision, and observing reward. So that's essentially the communication that happens back and forth between an application and the front end of our service. So at the beginning of a request, the application sends in the context. We respond with a decision, a randomized decision, and we observe the reward. Or the application reports the reward to us, rather. So the next step is you take all of this information and you log it correctly. And the logging part is done by something we call the join server. I'll go into details of all these pieces in a minute. So this is called a join server because there is kind of really a database join happening here in some sense, because usually what happens is that you know, you observe the context and you're required to almost instantaneously report the decision. But then the reward information usually might arrive with a if you're lucky, with a few seconds of latency. In many cases, maybe with a day or so of latency, right? Because it might just, the clicks might be going into a different stream, and then you have to sort of match the clicks to the request. So there is truly a join happening here. That's why the logging infrastructure is called a join server. And then once the join server has created this complete data set, we can do some learning on it. And we support both sort of incremental online learning that can just update the model in real time, or also batch learning, which can sort of, you can take a day or a week worth of logs and then just crunch through them to learn a new model. And then you find a new model that you actually redeploy using the client library to make improved decisions. Okay, so this is exactly exercising all the steps of the cycle we saw on the previous slide. So the client library is the part where the exploration or the randomization happens. The join server is definitely doing the logging bit. The learning part is happening in here. Again, I'll describe how we do the learning part. And then the deployment part is again happening actually through is being communicated from the learning part to the client library. And basically, the learn model is used to improve the quality of randomization going forward. So sort of one thing that I want to point out. So people often get kind of very shifty or very nervous when you use the term randomization, because they think we're going to serve users some completely arbitrarily bad content, right? And that's almost never the case, because even in theory, if you want to do well, then the actions that you choose amongst are the actions that might actually get a high reward in this context. And that's the reason why it's actually important to keep deploying improved models, because what the randomization algorithms will do is they will sharpen your randomization to focus on a better and better action set over time. As you learn more about user preferences, you narrow down the things that you're randomizing amongst, so that you never lose too much. You can very explicitly control how much you lose in the randomization part. Sometimes we also allow a slightly more complex learning loop. In fact, that is often required for many services, where so maybe you're updating your model in real time, but then maybe you have a lot of hyperparameters that you want to do more careful search over. Maybe you actually want to play with the featureization of the model at your own, maybe once a month or something. So you can, of course, like so there's a batch service that you can just spawn in the cloud that you can use to do all kinds of all kinds of data exploration of this form, and you can just push those settings into the online learning module. Right, so is the basic architecture kind of clear to people? Okay. So let's dig into the components a little bit now. So the first component is the client library. This is the front end of our service, which interfaces with your application. This is available in two forms. So it's available as a C++ or C# library. This is probably, if you have a application that requires decisions with very low latency, then this is probably the thing you want to use. I'll show an example of what it looks like roughly to use the C# version. And this is the version that, for instance, MSN did use, because they do care about latency, right? So this is optimized to be extremely quick. I'll show you some performance numbers towards the end. But it does require sort of writing some code to do the interfacing. So, and it does require sort of that wherever you're running your service, you should be able to sort of deploy some binaries, some code. So if you don't want to do that, if you don't want to hassle with any of that, there is also a web API that exists now. So you can just make an API call into our library, and that will return an action to you, a decision to you. As you might imagine, doing a web service call takes more time than just evaluating our C++ or C# library. So this does induce a higher latency, but is very easy to use. So it's a trade-off. we've implemented several exploration schemes. So I talked about randomization right now. So there's been a lot of research about how to do good randomization, and we've implemented some of those options, and that sort of set keeps on improving. In the experiment with MSN, we actually use the simplest and the most classical one, which is called epsilon greedy, where basically you have some deterministic policy, either machine learned or hand tuned, whatever you have. With 1 minus epsilon probability, you just follow what that says. With epsilon probability, you try something completely random. Right, so that's the simplest case. And then there are much more interesting randomization schemes that we also support. And the other thing that the client library ensures, so I'll point out a little bit later on. In order to do learning correctly in these scenarios, there are certain bits of information that it is important that you log. And client library, basically, because it communicates with the join server, it ensures that those bits are being logged. It just passes those bits along to the join server. So in some sense, it's nice because we don't have to rely on anyone else to ensure that the right bits are getting logged. We just log them ourselves. Right, so that's kind of a nice thing to have. So this is just actually, this one shows an example of interfacing not quite with the C# client library, but one level lower. But I just wanted to illustrate some of the aspects. So I'm showing this one. So basically, here we are creating an instance of the explorer so there is something called an exploration library, which is the most substantial part of the client library, which contains all these exploration algorithms. So we create an object of that. In particular, here we instantiate it with the epsilon greedy explorer with epsilon set to 0.2, and we have 10 actions. So we have sort of all the relevant parameters defined and being passed into our explorer. And then basically, so this is important. Each event is endowed with a unique key because you want to do joining later on. So it's important to create keys correctly. And then basically this is kind of all it takes. So you just call this routine called choose action. And what it does is it returns a randomized decision to you. Okay, and this might be based on, in this case, epsilon greedy exploration, either around a static policy or a machine learned policy. And you repeat this process for every request, every user request. Right, so that's very high level what it looks like to interface with the client library. Okay, then the second piece is the join server. So basically, the join server is again a pretty simple object. What it does is it has a temporal stream of data that's flowing in. Different data objects have different keys associated with them. It maintains windows of time, and within a window, all the objects with the same key are joined together. The window of time is flexible, so you can define what's right for your application. Typically, we ask, you think about what's the lag between when you have to make the decision and when you observe the reward, and that should be the time window for your join server. And what it in particular logs are, it definitely logs context. It logs the action you took. It's pretty important to log the probability with which you actually took this action. Otherwise, we can't do correct learning later on. And this is a part that often gets ignored. So recording this probability. So remember, we're making a randomized choice. So in this context, there are different probabilities with which we would have taken different actions. Then you picked one of them. Let's say action number 1. Then it's important to record what's the probability with which action number 1 was chosen, right? And then you obviously log the observed reward. You might have other data to log, so on, right? And in particular, the join server that we are using has been built on top of a service called Azure Stream Analytics, which is basically a stream analytics service that runs in the Azure cloud. It's pretty nice, very fault tolerant and scalable. So roughly what it looks like in the context of our application is something like this, right? So you have events coming in, right? So each time, whenever you see a key for the first time, it starts a time window, right? Maybe you see a new key, it will start another time window. Now within the green time window, if you see other green things, they are sort of, they will get associated when the timer elapses. right? So you have a timer basically associated with each key. When it elapses, then all the things associated with that key get joined. Similarly, you see some things corresponding to the brown key. When that timer elapses, they get joined and so on, right? So this is roughly how the join server flows to your data. Okay, so then there's the learning aspect. And really learning kind of has two interesting questions to ask here, which are both essentially addressed by existing contextual bandit algorithms. So one is actually a very simple task, that actually deceptively simple task, but is fairly challenging in this case. So maybe we've probably all had occasions where we have a current user facing system. We are unhappy with its performance. We think we have the $1 million idea that's actually going to improve the system. So how do we test this? How do we test whether our idea improves the system or not? Any thoughts? Right. So the more or less the industry standard way of doing this is to run an A/B test, right? So you code up basically an entire alternative version of the service that implements your idea. You divert some. You basically go and you beseech your higher ups to give you like 1% of the user traffic or something that you funnel through your idea, and if it does better than the status quo, then it might get deployed, right? Which means every time you had an idea that you want to try out, you have to maybe spend a month at the very least before it actually gets to the point where you know whether it works or not. It's pretty depressing. Now, the very powerful thing about contextual bandit learning is if you collect this randomized data, then you can just take the data you've collected and just use that data to evaluate what would have happened if you had deployed your idea without actually deploying it, just based on the offline logs you have. This is incredibly powerful. You cannot do this if you did not do a randomized experiment, but if you did do a randomized experiment, you can do this. Now, think about it. So you might have an idea. The idea might have some sort of a tunable knob, right? Maybe there are like 10 different settings you can set a parameter to. So if you have to run an A/B test, then maybe you try setting number 1, setting number 2, and so on. Maybe it's the 10th setting that actually gives you some traction. That's 10 months right there. With this one, you can just run a for loop over 10 choices, evaluate all those on your data. You know what happens. In fact, you don't even have to now maybe necessarily restrict things to 10 choices. Maybe you can just find the best choice over a continuous setting, right? And why stop there? In fact, you can maybe now think of your not just having one knob, but like we do always in machine learning, you can think of your knobs being weights on some parameters that you're trying to optimize, or maybe your knobs are actually the weights in a deep neural network or a boosted decision tree, right? And you can try to, just like we do in classical supervised regression or classification, you can actually go and fit the model to this randomized data. And what you're guaranteed is you're guaranteed that if your model has good performance on this randomized data set that you collected, then it will have good performance when deployed online. So this sort of offline certifiability of what happens online is just sort of beyond the reach of A/B tests, right? So this is, and you can make this very concrete. So speaking sort of in terms of statistical testing, you can show that the power of this test is roughly, it's exponentially larger than the power of A/B test. And you can make this statement very concrete. So this is kind of the main place where the contextual bandit techniques that have been developed over the last decade or so really sort of display their main strength. And in terms of the nice thing is that in terms of the true underlying machine learning software, you don't have to actually change all that much. There are only minor tweaks. So there are some simple data transformations that you have to do, after which you can just apply any regular multi-class classification algorithm. So if for the kind of models that you care about, you have a multi-class classification algorithm, you can just apply it after doing some simple transformations to your randomized data set. And we actually, in the Vopal-Wobbit toolkit, we definitely have an implementation of both the multi-class classification and the data transformations that are needed, and the papers describe the data transformations that are needed if you want to apply them with some other tool. And now, I mean, you can sort of abstract away everything, right? You can do online learning, you can do batch learning, you can do whatever type of model you want, you can do whatever features you want. All of those details sort of become abstracted away, and whatever techniques you apply for supervised machine learning can be applied. Okay, so that was basically what we did with MSN. We had some features based on the user demographics and their past preferences. We had a pool of 50 editorially chosen articles. So these were people sort of picking, based on the news stories available today, what are 50 most interesting ones, and then we had to let's still pretend we are just picking one out of these 50. And in fact, we weren't. So we were creating a ranked list. We were using epsilon greedy exploration, like I mentioned, and then the client library was basically picking based on exploration, picking this ranked list. The join server was joining the click stream along with all the contextual information, and we were basically just learning type of a linear model here, in fact. In an online learning loop. So we were, I think, yeah. So roughly, we were, I think, personalizing certain parts of this web page. Oh, yeah, the pointer doesn't show up, right? So we were personalizing, I think, this portion of the web page, and we had, I mean, just to give you an idea that this is pretty scalable. So there were tens of millions of users, thousands of requests per second. And there was not a substantial overhead on the front end machines from deploying our service, because that's kind of an important thing that came up when we wanted to do this. That, especially they're running, like the web servers are running this in multiple threads. So how much overall load are you going to add to the system? And not that much, really. And we were updating the models roughly every 5 minutes. So really, this is fairly online in terms of the learning loop. Like I said, with very minimal tuning, we got roughly 25% or so increase in clicks, and also across the board in the user engagement metrics. Okay, so that's kind of what we have today. There's a lot happening, and things are going to look a lot friendlier probably in the next few months. So really, what we are one thing right now, there's an upside and downside of having things modular, right? So upside is you can use whatever you want, you can pick and choose. Downside is you have to sort of go and provision each one of them individually, in particular because a lot of these are hosted in the cloud, so then you have to sort of individually provision cloud resources for them. So one thing that we are trying to create is simple push button deployment, that really you push a button, everything gets deployed for you. There are some default settings that automatically get configured for you, and you can just use it. And maybe we are trying to sort of incorporate as much parameter tuning just in an automated way as we can. One thing that we still haven't done is sort of, so we've made a lot of advances in the theory of contextual bandit learning, and some of the most exciting and sophisticated exploration algorithms we have from that literature we still haven't implemented, or at least not fully exposed to the library. And so that's probably going to happen in the next few months. And again, not all the pieces are quite externally available yet. So if I got you really excited, I have to apologize. You won't be able to try everything out just yet. Some important pieces are, so the exploration library actually is open source. It exists on GitHub. All the learning algorithms are actually open source also, and are implemented in this package Vopal-Wobbit. So really, if and the join server exists via Azure, that you can also try that out via Azure. And we have a website that's external that you can go and check the status of the project at. We have a project page with a lot of sort of more scientific details, some of the relevant research, some more expository slides and tutorials and so on. So a lot of resources. And yeah, that's all I wanted to say. So happy to answer any questions.